Hello, this video is about curved and flat mirrors. So it's about reflection. And we're going to start with just a brief overview of flat mirrors, plane mirrors, and you know a lot about these already. So if we have a flat mirror, and let's say we take a flashlight and we shine light onto that flat mirror, what's going to happen when those light rays hit the mirror? You probably learned this in middle school. You may not remember it, but you probably learned it at some point. And what we see is those light rays will reflect off, and the angle it comes in at, the angle each light ray comes in at, is the same as the angle it reflects at. And so what we have here is angle in equals angle out. And that's true for flat mirror, plane mirror reflection. So keep that in mind for this whole video. So if we take this idea and we use it to think about us looking into a mirror. So you're standing in front of your bathroom mirror. All right, so here's us, and we're standing in front of our mirror. How do you see a reflection of yourself? What's happening so that you can see a reflection of yourself? All right, let's start with your feet. What happens so that you can see an image of your feet? That must mean that there's light that comes from a light source. The light source provides light to your feet, and then from your feet, a light ray must go into your eyes so that you see it. But we have a reflection here. So there must be a light ray that goes from our feet to the mirror, and then from the mirror into our eye. And we know that this angle and this angle must be equal. Angle in equals angle out. How about our head? How do we see the top of our head? Same idea. There must be a light ray that goes from the top of our head, bounces at the mirror. Oh, I'm not doing a very good job of angle in equals angle out. But angle in equals angle out. And then that light ray says, okay, I can see the top of my head. But our brains do not figure out reflections. They don't figure out the bounces off the mirror. So when we see a light ray coming from this direction, our brain says it must be somewhere along this line. The source of that light, what I'm seeing, must be along this line. And same thing with the head. If there's a light ray going into my head, into my eyes here, then there must be a light ray that is along this line that is the source of that, what I'm seeing. I don't know how else to describe it. So if you do the geometry of this, knowing that angle in equals angle out, what you get is that, okay, I'm not a very good drawer, you know that. So what you get is that if angle in equals angle out, then the distance that you stand in front of the mirror is exactly the same as the distance that your image is behind the mirror. So when you're standing in front of your bathroom mirror, if you are hand's length in front, your image is hand's length behind. And so equal distance in front of the mirror, if the object is in front of the mirror, the image is equal distance behind the mirror. So suppose you want to look good for a job interview. You got a job interview coming up and you want to make sure you look reasonable for it. You stand in front of the mirror and you say, okay, do I look okay? If you're standing shaking distance, hands out distance from the mirror, you're seeing yourself at 2 arms length distance, because I'm arm's length from the mirror and my image is arm's length from the mirror. If you want to see what you actually look like to people when you're having a close conversation with them, step forward and get up close to that mirror. Get about halfway between what you're comfortable with and the actual distance you need to be. So if you're comfortable looking at your image here, step about halfway forward, and that's what your friends see. That's what the people who are actually talking to you pretty closely, we'll see. So that's what you should be looking at if you want to check and say, hey, do I look okay? So yeah, go try that. And you might be a little concerned. I don't know. It's not something I like doing myself. I like staying arm's width from the mirror. So that's flat mirrors. And the image we see of ourselves is equidistant behind the mirror as we are in front of the mirror. But we also can create images with curved mirrors. You've seen these curved mirrors in different places, like a convenience store. Up in the corner, they might have a curved mirror. If you're in Menominee and you're driving by the fire station downtown, then you're coming up to a T intersection, and that left-hand turn is a blind corner. So they put a curved mirror there. So how do curved mirrors create images? Let's figure it out. So we're going to start with this type of curved mirror, a concave mirror. And I'm going to put a horizontal axis here, just to give us some reference point, really. Suppose I have light rays that come in parallel. So light rays that come in all parallel to that mirror. What are they going to do when they hit that mirror? Make a prediction. Pause it if you need to. So let's think about what happens. So something like this. Well, when it hits this mirror, it doesn't know it's hitting a curved mirror. All it knows is it's hitting a mirror that's approximately at that angle. This is the tangent line if you're mathematically inclined. And so it says I'm hitting more or less a flat mirror like this. And so I'm going to bounce off at equal angles in and out. This one's going to do the same thing. I'm going to bounce off at equal angles in and out. And this one, and this one, and this one. All of those parallel light rays are going to come in, and they're going to bounce off this curved mirror, and they're going to converge. They're going to converge at this special point. This point right here, the distance from this to the mirror, that is our focal length. This right here is called F, our focal point. And that's really how we define a curved mirror. What a curved mirror is defined by its focal point. And its focal point depends on how curvy it is. So if I were to take a mirror that was less curvy, almost flat, what do you think would happen to that focal point? So make a prediction. If I take a mirror now and it's almost flat, let's do that center line. And now I'm going to do the same thing. I'm going to bring in some parallel light rays. Predict what's going to happen to that point where they all converge if I have a flatter mirror. Made your prediction? Okay. So what we should see, well, this is a little bit flatter, so it's going to go out to here. This one, okay, it's a little bit flatter, it's going to go out to here. If you predicted that that focal point would be farther out, you are correct. So for a flatter mirror, the focal point and that focal length is farther away from the mirror. So the curvature of the mirror really tells us the important bits about what we care about, that focal point. The focal point is related to the curvature of the mirror. A really curved mirror, so something like that, would have a very small focal, because you can imagine if this was a circle, all those rays would meet up about here. If it's really flat mirror, all those rays, okay, that would be like a circle this big, and so they might meet up around here. So the focal point of a curved mirror is how we really think about, that's the key piece of a curved mirror. Just like with a circle, the key piece of a circle is the radius. So the focal point for a curved mirror is the key piece. So how do curved mirrors actually produce images? Well, we can, oh, that didn't erase at all, my goodness. We can actually trace some rays and figure out how curved mirrors create their images. So if I can get this, wow, yellow to erase, the yellow wants to hang on a lot. Good to know for later, I suppose. Okay, so let's say we have a curved mirror. I'm going to draw that axis line, and the definition, the key point of that curved mirror is our focal point. So we're going to set it up like that. And now I'm going to put an object out here somewhere. And that object could be a light source, or you can imagine it as a person standing in front of a large mirror, whatever you want to do. I'm just going to focus on this point for now. Going back to how light behaves, light is emitted in all directions from a source. Just like the light that's coming down from this source hits me and is emitted in all directions. Because someone could see me if they're standing there, or there, or there. So there are lots of light rays that leave this point. If we follow a couple of them, we can figure out where the image is formed. Let's take a ray that goes in parallel. Well, we just decided that parallel light rays coming in all meet at the focal point. So this light ray is going to meet at the focal, and then keep going. There's another definition of the focal point, which says if a light ray starts along the focal and then hits the mirror, this is kind of the inverse description of a focal. If we have a light ray that lines up with the focal, it leaves the mirror parallel. And that's two. We have a third ray we can use. Sometimes people say, let's go to this point of the mirror, because if we hit this point of the mirror, we're hitting perfectly perpendicular. And so the angle in equals angle out. I'm not very good at figuring that out, at drawing angle in equals angle out. So I use another way to figure out how those light rays behave. And what I do is I use a really interesting relationship between the focal and what we call the center of curvature. If this were a full circle, then the center of the circle would be right there. It turns out that the focal length is exactly halfway between the outside and the center. So the focal is half of the center of curvature, or you can think of it as the center of curvature is 2 times the focal length. So there's this thing called the center of curvature, and it's double the focal. Okay, I don't think I did that very well. If you're making notes, try to make it double, because it should be double. Mathematically, this is the case. So we can have another light ray that goes through the center of curvature. Oh boy, I really messed that up. Let me try again. I didn't even hit the center of curvature very well. There you go. We'll call that good. Now when that center curvature hits our curved mirror, we have a light ray that goes through the center curvature. Okay, my drawing skills aren't very good today. Let's say, bigger center curvature. If we have any light ray that goes through the center of curvature, through the center of that circle, and then hits that mirror, hits that curved mirror, at what angle is it going to hit the mirror? Well, if it's at the center of the mirror, center of this circle, it turns out it hits it right at 90 degrees, perpendicular, which means that it comes in and it's going to bounce right off on the same line. So we have a center curvature line that goes down here, but it also bounces boom, right back out. And now we have a very interesting place. We have a place where these three meet. Not very good here. If you're doing this on your own, I hope they meet a little better. But where those three rays meet, it's all the light that leaves this point. All those light rays come together again, and this creates an image of that object, whatever our object was. And so the image created of this object is formed here. And if you were to do something like the hand here and do the same thing, you would see that the hand forms about here. So what we see, oh boy, not to scale at all. What we see in a big curved mirror is an upside down image of ourselves. And sometimes that image could be bigger, sometimes it could be smaller, depending upon the distance we are from the mirror. Just going to take a brief pause real quick. Okay, computers, you know, they want to update at random times. So, we have an object here that is upside down, inverted, and sometimes it's smaller, sometimes it's bigger. If you want to test this, go get a spoon. If you have a spoon that's really shiny, then look at yourself inside the curved side of the spoon. What you should see is an upside down version of yourself. Go give it a try. Now, we can also say, all right, what happens if we are really close to that spoon? Again, if you have a spoon that's nice and shiny, bring that spoon real close to your nose. See what happens to your image. What do you see when you bring it really close to your nose? So when we are very close to a curved mirror, a concave curved mirror. So this one is concave because it's curved inwards. So if you got the spoon, give it a try. And then we're going to do the same kind of light ray analysis for yellow man, for close to a curved mirror. All right, I think I just got to call this good. So we have a curved mirror. I'm going to do my horizontal axis again. And now we're really close. We're going to have an object close to the mirror. And so I'm going to say my focal is here. And I'm going to put an object real close to the mirror. So let's do the same ray analysis, light ray analysis. We're going to have a light ray that goes out parallel, and all those parallel rays that hit the mirror, they go through the focal. Okay. And then, if we have a light ray that lines up with the focal, when it leaves the mirror, it's going to leave the mirror parallel. And our third one, again, you could go angle in equals angle out, but what I tend to do is say, well, if I use the center curvature, which is 2F, then I only have to draw a straight line ray. Okay, 2F, that's like way over here. So if I do a light ray, that's way over there. It's going to be something like, whoo, and it goes in and out along that same line. Okay, so the light rays that leave the mirror, this one, this one, this one, they're not going to converge. They don't meet anywhere. Or do they? Or do they? So here's one of the light rays. Here's a second. Here's a third. These three light rays are leaving the mirror. We can actually find where they would converge if they actually did. See if you can figure out where those three rays, this one, and this one, where would those three rays meet up if they could? Did you guess up here? Because that is correct. What we can do in this case is backtrace where those light rays act like they come from. So again, this light right here, it leaves the mirror like this, and our eye is fooled into thinking that the light ray comes from somewhere along this line. The light ray from the center curvature, and again, this light ray, our eye thinks it comes from along that line. This one, okay. Yeah, or straight lines. Those are straight lines. Pretend they're straight lines. So where these three lines meet up, right here, that's where our image would be formed. But the light rays aren't actually there. The light rays don't converge there. If I put a screen or a piece of paper or a card behind the mirror, could I see the light rays on the mirror? Of course not. It's behind the mirror. And so what we do is we call this a virtual image because it doesn't exist in reality. You can't put a piece of paper there and see it. But if you are standing over here in front of the mirror, your eye gets fooled into thinking that all these light rays that are coming into your eye are produced right here. So this is a virtual image. And take a look. This is above the axis, just like this one was above the axis. So it is an upright image, and it is bigger than its original object. So it's magnified. It's bigger than the object. So if you take a shiny spoon and bring it real close to your face, you should see an image of your nose that is upright in the regular orientation, and the nose should be magnified. That's what you should see if you bring a spoon real close to your nose. So that's the second type of image we can create. What is the third type? We have 3 different types of images that we can create with curved mirrors. So we've been talking about concave mirrors. Whoops. Ooh, that was a good catch. Now we're going to talk about convex mirrors. So, convex mirror, what would that look like compared to what we've been dealing with? So hopefully, if you have your spoon, you're going to flip that spoon over. Now we're dealing with something where the mirror is on the outside, the reflective surface is on the outside of the curve. There's our axis. If we have parallel light rays coming in, so I got a parallel light ray coming in, it's going to hit and it behaves like it's a flat mirror there, so it's going to go up like that. Parallel light ray coming in here, all right, it's going to go off like that. Something like that is going like there. So what we have here is those light rays that come in parallel are all getting spread out now by this reflective surface, by this mirror. They are being diverged. So for a convex mirror, where would those light rays all meet up? Well, they don't meet up over here, but if we could extend those rays backwards, what we would find is that all those light rays meet up right there. And so a convex mirror has a focal point that is behind the mirror. It's a virtual focal point. So virtual focal. And that means that we can't have a real image formed, because a real image is formed when the light rays actually converge at a point. There's no way that this mirror can actually converge things. So we can't get a real image from a convex mirror. But what can we see? So let's try this ray tracing again. I'm going to grab my mirror and do that. There's my horizontal axis. Oof, not very close to the center of the mirror. Doesn't matter. Now we're going to have an object that is out in front of the mirror, but that mirror has a focal point back here. And mathematically, when we're talking about a virtual focal point, we give it a negative sign to say it doesn't really exist. It is a virtual focal point. That negative sign tells us it's virtual. All right, so let's figure out what these light rays do. We've got a light ray that comes in parallel. It hits here. Okay, and it's going to bounce off like that. And it's going to bounce off in a line with the focal. Again, these rays must diverge over here because that's the job of this mirror. we have a light ray that goes, okay, can I do the center curvature here? And center curvature, double the focal, out there. So if we had a light ray that aims at the center curvature, then it's going to bounce off the mirror at 90 degrees, and it's going to bounce off exactly on itself. So the center curvature line is just, if it's aimed at the center curvature, it bounces back on itself. The third one is the harder one. So if you go back to the other type of mirror, we had one that was through the focal, that lined up the object in the focal, and then bounced off parallel. How do we do that here? How can we do that here? We're actually going to do the same thing. If you have a light ray that aims at the focal, so it aims at the focal, as soon as it hits that mirror, it turns out it bounces off parallel. But it's aimed at the focal. And wow, this is not going to meet up. This is pretty terrible. I'm so sorry. Let's do that. And center curvature, like, whoop, 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 like that maybe. And then this one. It turns out that those three rays, they leave the mirror diverging, because that's what this mirror has to do. We got one there, one there, one there. They spread out. But if we could trace them back, if we could use our eye to trace them back, our eye would say, hey, all of those light rays come from this point right here. So if this was a person standing in front of a curved mirror like this, what we would see is a very tiny person, but upright and much smaller. So if you flip your spoon around, you should see an image of yourself that is upright, not inverted, not upside down, but upright and tiny. So to just pull it all together, make a summary, what we can say is for a concave mirror, if we are far away from a concave mirror, then what we see is an upside down image, and it could be bigger or smaller. We don't know. It's not always the same thing. And this is called a real image because those light rays coming in are actually converging down. You could put a screen or a piece of paper at a point and see that image. If we're close up to a concave mirror, then what we have is an upright image. It's right side up, and it's bigger than normal, and this is what we call a virtual image. A virtual image, because the light rays don't actually exist behind the mirror, but our eyes fooled into thinking that they do exist. And then if we have a convex mirror, and turns out if we're anywhere in front of a convex mirror, we have an upright image, but it's tiny, so it's smaller than our object. And again, it is virtual because the light rays don't actually meet here, but our eye gets fooled into thinking that there is an image behind the mirror. So that is an introduction to flat mirrors and curved mirrors. Thanks for watching.